The dominating set, an NP-complete problem, presented by Henry Hetzel. The dominating set problem describes a set of vertices in a graph that result in every vertex outside of the given set to be adjacent to a vertex inside of the set. The goal of the problem is to find the domination number in the minimal dominating set, and there are several algorithms that can be used to approximate a solution to this. As you can see, the figure to the right shows several examples of dominating sets for a given graph. The dominating set of some graph, G, composed of the set of vertices and the set of edges, is a subset D of the vertex set V. Every vertex of V that is not in D must be adjacent to at least one vertex of D. The domination number is the smallest possible cardinality, or number of elements of this set. Domination sets are closely related to independent sets, and any given independent set will also be a dominating set if and only if it is a maximal independent set. This means that any maximal independent set in a graph is a minimal dominating set as well. The domination problem began to be studied in the 1950s, but interest in the problem increased noticeably in the 1970s. Proof that the domination problem was NP-complete came in 1972 when Richard Karp, a Turing Award recipient, proved that the set cover problem was NP-complete. Since there are straightforward bijections between these two problems in the form of vertex to set and edge to non-disjoint intersections, it was clear to Richard Karp that the dominating set problem was NP-complete as well. Applications of the dominant set problem. Dominating sets can be useful for internet routing problems. By calculating an approximation of the minimum dominant set for a network, a business can find the minimum number of internet routers needed to ensure every computer has access to the internet. This means that businesses can reduce the expenditures for internet routers and ensure that every user on their network has the internet they need. In addition, by converting neighborhoods and school bus routes into graphs, the dominant set can ensure that bus rides are efficient and mean that students receive the shortest and timeliest routes to their schools. This will mean that parents don't have to worry about their students having long bus rides or in making sure that their students have to be at bus stops earlier than would be reasonable. Approximation algorithms for the dominating set. There are several algorithms that can be used to find the minimum dominating set for a graph. One such approximate algorithm, found by Fabian Kuhn and Robert Wattenhofer in Resource 2, is based on linear programming relaxation techniques. Their algorithm achieves a non-trivial approximation in a constant number of rounds based on a maximum node degree. Linear programming relaxation is used to design approximation algorithms based on the concept of the integrality gap, which is the maximum ratio between the solution quality of an integer problem and its relaxation. Approximation algorithms continue. In addition to the previous technique, greedy approximation algorithms can also be used to find the minimum dominant set if the graph has a maximum degree of delta. This algorithm finds that the cardinality of the dominating set is less than or equal to n plus 1 minus the square root of 2m plus 1, where n is the number of nodes and m is the number of edges in the graph. Quantum algorithm. Reference 1 provides efficient quadratic unconstrained optimization, or QO, formulations for the dominating set and edge cover combinatorial problems suitable for adiabatic quantum computers. The paper claims that the number of qubits required to solve the dominating set problem is in the order of n plus n times log of n, where n is the number of vertices in the set. In conclusion, the domination set problem is an important NP-complete problem to understand and apply to real-world solutions. Dominant sets can ensure maximal short-range coverage in all types of scenarios, where it is important for a set of vital vertices to be connected to all other vertices in the graph. With applications ranging from internet coverage to school bus routes, it is clear to see why so much effort has been put into finding the best solutions to this problem. Thank you.